All right, so chapter 2 was focused on an introduction to matter. And the first thing we did was look at how we can classify matter based on its composition. So this flowchart or tree diagram, whatever you want to call it, should look familiar to you. We used it extensively in the beginning of the year. Matter is anything that occupies space, right? So has volume and has mass. And will exist in one of three phases: solid, liquid, or gas, mostly. Matter can be broken down into either being classified as a pure substance or a mixture. Pure substances having an invariant or invariable chemical composition with distinct properties, where a mixture is matter consisting of two or more pure substances physically just mixed together that are retaining their individual identities and individual properties. They can be separated by physical methods. Now, when we talk about a pure substance as having an invariant chemical composition, we mean that the composition of the substance is definite, essentially. So, gold is gold and will always be gold, made up of just gold atoms. Water will always be H2O, made up of water molecules. But a mixture, example I like to use a lot is if you're making something like tea or iced tea, that everyone can have a different mixture they call iced tea, but some may have more water, some may have more tea, some may have more sugar. The ratio in which you're combining the things into a mixture does not matter, but the ratio does matter for a pure substance. Pure substances can be further classified as elements or compounds, and then mixtures can be classified as homogeneous and heterogeneous, and the definitions are there for you, but you should be familiar with them already. We define chemistry as the study of matter, the changes it undergoes, and the energy involved in those changes. And you should really have seen that the year was split amongst the sort of different thirds of that definition there. To study chemistry, we use observations, inferences, and hypotheses, remembering the difference between those three. Observations is anything we can say about matter using our five senses. An inference is some sort of a mental judgment based on prior knowledge. And then a hypothesis is really an inference, but reworked in an if-then format, which allows us to then go and study that inference or the question that we posed about a specific observation using a set of controlled experiments. It sets it up so that we can study it, essentially, to try and come to some sort of a conclusion or have some sort of justification for what we are seeing or what is going on. Matter, again, we define as anything that has mass and takes up space. We can classify matter based on its composition, like we did up here, or also based on its properties. So the composition has to do with what the matter is made up of, where the properties are really talking about distinguishing attributes or qualities about a substance. Not everything in the universe is considered matter. If it's not, most likely it's going to be energy, like light or heat, electricity, fire. Those are some of the examples we looked at as being energy, not matter, in the beginning of the year, because they do not have mass and do not take up space. But some other things that would not be matter and not considered energy would be things like memory or reflection or love, feelings, things that are not tangible, that don't take up space and don't have mass, would not be considered matter. If we break down that definition of matter even further, mass is the amount of matter in a substance, where volume is the amount of space that the matter occupies, and there are some of the units, the important units that we use throughout the year. We also classified matter based on its physical state: solid, liquid, gas. Aqueous is an additional one that we should throw in here. Remember, aqueous is a really specific phase of matter that shows something was dissolved in water. We took a look at something that I like to call the chemistry triangle. Really hones in on how chemistry is studied and why chemistry can be so difficult. Really, chemistry is about taking macroscopic observations, so things that we can see, and then trying to explain those observations on a level which we cannot see. And that disconnect is really what makes chemistry so difficult, but we use a symbolic level to bridge the gap between those two. So we use formulas, symbols, diagrams, equations, all of those things to help us bridge the gap between the macroscopic and submicroscopic scale. We looked at properties and changes in matter. physical properties versus chemical properties. Remember, a property is an attribute, something we can say about matter, the way we can describe it. A physical property can be observed or measured without changing the identity, but a chemical property, if it's observed and measured, is going to change the identity of that substance. A chemical and physical change is altering the matter in some way, shape, or form, but the difference between a chemical change versus a physical is that in a physical change, the matter changes only form, but not chemical identity or composition. And in a chemical change, the change that's occurring is changing the composition and the identity, hence creating a new substance. So there are some examples of both chemical and physical properties, and then chemical and physical changes for you. We then looked at separating mixtures. Mixtures, we said, are physical combinations of pure substances, so they have to be separated physically, right? There's no new substance that is formed in a mixture, so they're fairly easy to separate. We looked at some methods like magnetic separation if the substance is magnetic, distillation to separate liquids based on boiling point, evaporation. If there's a solid dissolved in a liquid, we can evaporate or boil the liquid off and be left with whatever solid was dissolved. We looked at filtration. If we have an insoluble solid that can be caught by filter paper. We looked at decanting, which is a quick way. It's sort of like, I call it the lazy man's filtration. It's essentially doing the same thing minus the actual filter. And then chromatography, we looked at a little bit in solutions, is a way to separate substances based on their intermolecular forces, really. There's a mobile phase and there's a stationary phase, and the mobile phase goes over the stationary phase and separates the substance based on the intermolecular forces of the substances that make it up. So a common example for chromatography is looking at ink. So this little black dot is black ink. The liquid solvent here is the mobile phase. As it goes up the paper, which is the stationary phase, it dissolves some of that ink, and the components that make up the ink will continue up with the stationary phase, but it is sort of like a competition of intermolecular forces. If the individual components of the ink are more attracted to the solvent, it's going to go with the solvent as far as it can up the paper. But if the intermolecular forces cause these substances in the ink to be more attracted to the paper, it's going to stay lower down on the paper. It's not going to be able to be pulled by the solvent. So they're separated based on their intermolecular forces. The last couple of things we looked at were some important laws of chemistry. So the law of definite proportions, the idea that when a compound is formed, it's going to form in the same ratio every single time, and that ratio is going to be a low whole number ratio, right? There's no fractions of atoms that exist. And the law of conservation of mass, or law of conservation of matter, the idea that matter is not created or destroyed in a chemical reaction. Whatever atoms we start with, we have to end with. They can unbond, rebond, rearrange, but the mass that we start with has to equal the mass that we end with, even though it may look like mass has been lost or gained. Doing everything in a closed system will help ensure that we can get a good result if we're trying to prove the conservation of matter. And then the very last thing we touched upon were the difference between a hypothesis theory and law. Hypothesis we went over a little bit already in this review as a possible answer to a question, right? If this happens, then this is going to happen. Those stem from observations. So as scientists, we question things that we see. We observe things and then we question those observations, why something is occurring. And that may lead us to come up with a hypothesis, a possible answer to the question that we pose. And then we may experiment to see, is that hypothesis correct? Can we confirm, or do we have to deny the hypothesis? Now, eventually we may develop one or two things. We may develop a theory if that hypothesis has undergone enough experimentation and has been supported enough by experiments. A theory is just a hypothesis that has been tested and supported many times. And the most important thing is that a theory attempts to explain how or why something occurs the way it does. Where a law is just a general statement of fact that describes some observation that we see over and over again, or some pattern, right? It doesn't attempt to explain why. It doesn't attempt to explain how, it just attempts to explain that it does. So the law of conservation of mass is a law because we observe every single time that when we start with a certain number of reactants, we end with the same, or certain grams, certain mass of reactants, we end with the same mass of products. Now, atomic theory then helps to explain that law by saying, well, we have things called atoms, and all matter is composed of atoms, and those atoms are whole units, and those atoms can only rearrange, right? So that's the important difference between hypothesis theory and law. And the only thing I'll leave you with is that the scientific method, as it's taught in elementary school or middle school, is often taught as this list of steps that when you get to the end, we can make a conclusion or draw a conclusion, it's over. And that's really not how it works. It's a really iterative process. So we question our observations, and then we either come up with a law because we've observed the same thing so many times, or we come up with a hypothesis to attempt to explain why we are observing what we are observing. We run experiments, and if we run enough experiments that are supported, that hypothesis is supported enough times, then we can come up with a theory that attempts to explain how or why the observations we are making make sense. So that brings us to the end of Chapter 2, Matter, and you should be now ready to take your Chapter 2 throwback quiz.